This is lecture 10 in BBSP 610. We're going to be discussing random variables in the normal distribution. The first part of this lecture focuses on random variables. I'll warn you in advance that it's kind of technical and kind of dry and not something you will use in your day-to-day life as a bench scientist. That said, it's kind of important to at least understand the terminology when we talk about the normal distribution and just understand the terminology when you see it generally. So bear with me for a minute. We'll get to the useful stuff shortly. But a random variable is defined to be a variable that takes on different numerical values depending on the outcome of some random process. For example, you could roll a die and see how many spots are on the die. And you can make probability statements about this random variable. But for example, the probability of rolling a 4 is 1 out of 6. The probability of rolling something between 2 and 5 is 3 out of 6, or 1/2. You could also define what's known as a continuous random variable. I'll define that formally here in a minute, which can take on a continuous range. You could say the height of a given male selected from a certain population, and that could theoretically be any possible value within reason. So you could say the probability between 65.2 inches and 70.4 inches is about 0.46. So a discrete random variable is a random variable that can only assume a finite number of outcomes, number of spots on the die, number of heads when you flip a coin several times, etc., etc. Whereas a continuous random variable is a random variable that can assume infinitely many different values. Height, weight, gene expression level, anything that's where the outcome could be on a continuum. If you could measure height with perfect accuracy, theoretically you could go out to 1,000,000 billion decimal points. In practice, of course, you can't do that, but in theory, it's a continuous range. So, for a continuous outcome, we usually say the probability of an exact of any given value is 0. That if you measured me with perfect accuracy, my height wouldn't be exactly 73 inches. It would probably be 73.45721, who knows, something like that, inches. So we assume the probability of any specific value for a continuous random variable is 0, and we only define probability for ranges. So we would say the probability that I'm exactly 73 inches tall is 0. We could talk about the probability that I'm between 68 and 74 inches, for example. A density function gives you some idea of which values in a distribution are most likely. That it basically shows the proportion of values of that particular random variable that fall within a specific range. For example, on this slide you see a discrete density function. It's saying you have about a 23% chance of having the value 0, slightly over 30% chance of 1, a little less than 30% chance of 2, etc., etc. A continuous density function, as I said before, we assume the probability of one specific value is 0. Instead, the density tells you the probability of being within a specific range. If you wanted to find the probability that you're between 68 and 74 inches, for example, if the bell curve you see on this graph represents the distributions of heights, you could find the probability that you're between 68 and 74 inches tall by looking at the range, by calculating the probability that you fall within the shaded blue area on the graph. And for a discrete random variable, all probabilities have to sum to 1, and for a continuous random variable, the area under the curve has to be 1, because, as I said, with probability in general, sum of probabilities always have to be 1. So we define something called the expected value of a random variable. expected value is in a certain sense the mean value of the random variable. That if the random variable can take on values x1, x2 up to xk, then the expected value of x is defined to be x1 times the probability of x1 plus x2 times the probability of x2 and so on, xk times the probability of xk. Simple example, say you roll one fair die, count the number of dots, and the expected value is 1 times the probability of rolling a 1, which is 1/6, 2 times the probability of rolling a 2, which is 1/6, etc., etc. The probabilities of all of them are 1/6, so the expected value is 21 divided by 6, which is equal to 3.5. A slightly more complicated example, let's say that you run a clinic for preschool children and you know that about 58% of the children who come to your clinic will have no ear infections in a year, 27% will have one, 9% will have two, etc. If you want to calculate the expected number of ear infections per year that a child will have in your clinic, that would be 0 times 0.58 plus 1 times 0.27, etc., etc. Add that all together and you get 0.64. The variance of a random variable is the square of the standard deviation of the random variable, and you calculate it as similar to how you would calculate the standard deviation, that you take the value, a given value of the random variable minus the expected value squared times the probability. So x1 minus the expected value squared times p1 plus x2 minus the expected value squared times p2. Add all those together. So the dice example again, we know the expected value is 3.5, and it looks like my subscript got messed up when I converted this to PowerPoint. I apologize for that, but it's 1 minus 0.35 squared times 1/6 plus 2 minus 3.5 squared times 0.6, etc., etc. Add all that up, and it comes to be about 2.92. Similarly, if we want to find the number of ear infections per preschool child, that would be 0 minus 0.64 squared times 0.58 plus 1 minus 0.64 squared times 0.27. Again, add all that up, and it comes out to be 0.830. To find the expected value, these formulas that I just gave only work for discrete random variables. It's possible to define expected value and variance of continuous random variables, but you have to integrate stuff. I don't want to torture you with that much math for something that isn't essential to this class, so we're not going to talk about it. I'm just going to mention in passing that it's possible to do. And a couple properties of expected values that come in handy from time to time is that if x is a random variable and a or b are constants, if you want to find the expected value of a linear transformation of a, that is a plus b times x, you can just take a plus b times the expected value of the original random variable. Similarly, if x and y are two different random variables, the expected value of x plus y is the sum of the individual expected values. I'll give some examples of this in the upcoming slides. So, for example, let's say that you're running a clinic again, and X is the number of vaccines you administer per day, and Y is the cost of a vaccine. And let's say it costs $250 per day just to run your clinic, and each vaccine you give costs $3. If the expected number of vaccines that you give in a given day is 120, then the expected cost in a given day is 250 plus 3 times 120, or $610. And there's also a formula for linear transformations of variance. If x is a random variable and a and b are constants, and you want to calculate the variance of a plus bx, a, it turns out, doesn't matter at all, which makes intuitive sense because variance measures the amount of dispersion in a random variable, so if you shift the data to the left or to the right, the dispersion doesn't change. But if you multiply it by b, then the variance is multiplied by b squared. The second rule is if x and y are independent random variables, then the variance of the sum is equal to the sum of the variances. That only works if x and y are independent. That formula does not hold in general if they're not independent. So, linear transformation vaccine example again, say you want to find the variance in the cost of vaccines. If we know that the variance in the number of vaccines that is administered is 225, then the variance in the cost be 3 squared times 225, which is 2025, so the standard deviation of the cost would be the square root of that, or about $45. And one property of expected values and variances that's kind of nice is if you want to find the expected value or variance of a mean, the expected value, if you take, just to be clear about what I'm talking about here, say you grab one person off the street and measure how tall they are, that measurement will have an expected value and a variance. Let's say you grab 100 people off the street and take their mean, and you want to find the expected value and variance of this mean. Well, your intuition might be that the mean of 100 people, or the expected value of 100 people, should be the same as the expected value of one person, but the variance should be smaller. If I happen to grab, say, LeBron James off the street, I'll get an unusually high measurement for the mean, but the probability of grabbing 100 LeBron Jameses off the street is very low. I should get something that's closer to the true population mean. It turns out that's exactly what happens, that the expected value of the mean is equal to the expected value of an individual observation, but the variance of the mean is equal to the variance of an individual observation divided by the number of things that we're taking the mean over. So when we take the mean, the expected value remains the same, but the variance gets smaller. And I'll note in passing that there's a property called the law of large numbers, which says that you select a bunch of independent observations from the given population. As the number of observations increases, the sample mean will approach the population mean. Which makes sense. If I grab one person off the street, I might get LeBron James, but if I start to grab 100, 1,000, 10,000 people and measure their heights, their mean height will become closer and closer to the population mean. This picture here shows a computer simulation where they tried this, or they just looked at the proportion of heads in a simulated, when they simulated tossing coins. And early on there were a lot of extra heads, but over time the true proportion, or the observed proportion of heads, became very close to the expected proportion of heads. So, now we're going to talk about the normal distribution, which is far and away the most important distribution when you're doing statistics on a day-to-day basis. The normal distribution are a set of symmetric bell-shaped distributions that are described by their mean and standard deviation. Below is the formula that's used to graph the density of the normal distribution. It's not something we'll use in this class. In upcoming lectures, I'll explain why the normal distribution is so important. And as I said, the shape of a normal distribution depends on its mean and standard deviation. Well, actually it depends on the standard deviation. The mean gives the center of the normal distribution. The standard deviation gives you how spread out it is. If the standard deviation is small, you have a really steep bell curve centered at the mean. If the standard deviation is larger, then it's bigger and flatter. So let's say, for example, that we have a population of fish and the lengths of individual fish have approximately a normal distribution with mean 54 millimeters and standard deviation 4.5 millimeters. Let's say we want to find what proportion of fish are less than 60 millimeters. Well, as I said before, you can do this by finding the area under the appropriate normal density curve. The graph on this page is the density curve for this population of fish that I just described. The probability that a given fish is less than 60 millimeters, you would find the area of the curve under 60 millimeters. The way you would do that is using integration, but that would be a painful integral to calculate by hand. Luckily, it's easy in R. The command in R is called pnorm. I'll explain this in more detail on the next slide. But pnorm says the probability of being less than 60 in a normal distribution with mean 54 and standard deviation 4.5. In this case, it's about 90.9%. The general syntax for pnorm is pnorm q, mean, sd. That computes the probability that a normally distributed random variable with mean, and standard deviation sd is less than q. So in the example I just gave you, pnorm of 60, 54, 4.5 is the probability that a normal distributed random variable with mean 54 and standard deviation 4.5 is less than 60. And we can do this for more complicated probabilities than just less than 60. Let's say we want to find what proportion of fish are more than 51 millimeters long. In this case, that would be the area of the graph above 51. Well, pnorm will only give us the area of the graph below 51, the white portion, but we want the red portion. We can easily calculate the red portion by taking advantage of the fact that the area under the entire curve has to be 1. So we just say 1 minus pnorm 51, 54, 4.5. That means we subtract the white portion of the graph from 1. We're left with the red portion, which is about 74.75%. And we can extend this further. Let's say we want to find the percentage of fish between 51 and 60 millimeters. That would be the red portion in the middle of the graph here. And you can probably see how we might do this. We could take the area to the left of 60, which would be pnorm of 60, and then subtract the part that's to the left of 51, which would be pnorm of 51. So you can see the command here, pnorm 60, 54, 4.5 minus pnorm 51, 54, 4.5. It's about 65.6%. Let's say we want to calculate the quantiles of the normal distribution, that we want to do this in reverse. Let's say we want to find the 70% quantile of the fish distribution, the value such that 70% of the fish will be less than this. Before we had computers, this was really painful to calculate, but now it's easy in R. The command to do this is called qnorm. That if you want to find the 0.7 quantile of distribution, you can say qnorm 0.754 4.5. Turns out to be the 70% quantile is about 56.36. In other words, 70% of the fish will be less than 56.36 millimeters. And to give you a preview of coming attractions, let's say we want to find a 95% confidence interval for a size of a single fish that we pull out of the lake. We want 95% of the fish to be between the upper and lower confidence bounds. So, well, 95% of the fish will be between 2.5% and 97.5% quantiles of this distribution. So let's use qnorm twice. The 2.5% quantile is 45.18. The 97.5% quantile is 62.82. Oh, the 95% confidence bound will go from about 45.18 to 62.82. In future lectures, we'll discuss how to calculate this for means and other derived statistics of interest, which is what you'll usually do in practice. And I'll note briefly that sometimes you'll want to standardize variables. This is called converting them to z-scores. which means that you just take the value of the variable, subtract the mean, and divide by the standard deviation. You can think of it as the number of standard deviations you are away from the mean, whether you're above it and have a positive z-score, and below it and have a negative z-score. So you'll notice, for example, in R, if so you'll notice these two commands give identical results, that if we calculate the proportion that's less than 60 for a normal distribution with mean 54 and standard deviation 4.5, we get about 90.9. But if instead we convert it to a z-score, 60 minus 54 divided by 4.5, for a normal distribution with mean 0 and standard deviation 1, we get exactly the same probability. And you're probably wondering, what's the point of this, Eric? Well, back before we had computers in R, the only way that you could calculate probabilities using the normal distribution was to use tables. And so you couldn't create a table for every possible value of the mean and variance. Sorry, naturally they decided to test the fire alarm during the time I was recording this lecture. But as I was saying, before we had computers, you couldn't possibly create normal tables for every possible value of the mean and variance. They created one table for when the mean was 0 and the standard deviation was 1, and you converted everything to a z-score to calculate the probabilities. Nowadays, we just use R, so it's not that important to know how to do this. I mention these z-scores just because you'll still see them in paper sometimes. You'll occasionally use them for other purposes, such as comparing measurements on different scales. Well, things to remember for today's lectures are that random variables take on numerical values depending on the outcome of a chance operation. You can calculate their expected values and variances. Normal distributions are a bell-shaped distribution that are defined by their mean and standard deviation. Given the mean and standard deviation, we can compute probabilities in quantiles by taking area under the normal curve, which is easiest to calculate using R. And the R commands that you use to do this are called pnorm and qnorm.